expressions here, and we have to impose a slight restriction here. We have to say that this real number k is greater than or equal to 1, right? Otherwise, we'd be taking the square root of a negative number. All right, you can't really order the complex numbers, so we're going to assume that k is greater than or equal to 1, and k is just a real number. Now, again, we're trying to find out which one of them is bigger. So what we're doing here in this expression is we're multiplying through by 1, and this is kind of the miracle of math. If you can multiply by 1 in a clever way, you can usually transform something, or often you can transform it into something that's more manageable. Now notice right here we've created this form a minus b times a plus b. This is like one of the most well-known algebraic identities around, the difference of two squares. So you have a minus b as one of the original comparison expressions. Okay, and then this is going to be times a plus b. All right, and nice things happen, as you can see, because this is equal to a squared plus b squared, which is just the numerator right over here. Okay, so this is equal to a squared minus b squared right over here. Now it looks nutty, like how in the world could that be equal to 1? But if you just know what your a is the square root of k plus 1. When you square that, you get k plus 1. And similarly for b squared. B would be the square root of k. When you square it, you get k. So k plus 1 minus k is just the 1 you see right here. And that's good news, because it makes it easy to compare these numbers. It makes it easier to compare the two numbers. Now notice, this guy right here, since we multiplied it by 1, is just equal to this, okay? But now a very nice thing happens right here. You can see that this denominator right here, this denominator, the square root of k plus 1 plus square root of k, is larger than this denominator right here. So that makes this expression smaller. Okay, again, folks, this denominator, I'll just circle it. This denominator right here is larger than this denominator here. Okay. See if I got that. Yeah. So again, folks, this circled expression is larger than this circled expression right here. So that makes this guy right here the larger number. That makes the square root of k minus the square root of k minus 1 the larger number. I'll just go ahead and write that down. So what we have right here is the square root of k plus 1. Should have just written it down from the beginning. The square root of k plus 1. Let me get that extended just a little bit there. The square root of k plus 1 plus the square root of k is strictly greater than the square root of k square root of k plus the square root of k minus 1. And y'all would kill to learn how to make this screen not move. It irritates the hell out of me. I don't know why it does this. Okay, square root of k minus 1. Okay, now that is why this statement is true right here. Now let's look at just a special case. Let's say that we had, let's say k equals to 14. So we'll do k equals 14 right here. Okay, this gives you the square root of 15 right here, right? Square root of 15 minus the square root of 14. Is going to be less than. And this was shown on the CyberMath channel. What I'm showing you is just a generalization of what was shown at CyberMath. So this is the square root of 14 minus the square root of 13. I know everybody's reaching for their calculators. It's a very sharp inequality. And if you think about the shape of the square root graph, you can kind of see why this is true. I'll go ahead and get that in parentheses if you want. Okay, but again, what I've shown you is just a generalization of a special case shown at the CyberMath channel. Okay, and y'all, if you think about it, just want a little bit more commentary here. This is very related to calculus. Like if you let f of x equal to the square root of x, I won't go through all the steps, but you could show, it's not hard to show that f double prime is less than 0. Notation is great here, isn't it? You drag the 1/2 around to the front, and it'd be minus 1/2. Then when you do the second derivative, you're going to get that it's less than 0. Okay, less than 0. Okay, but what that means is that the graph of f of x is increasing at a decreasing rate. And so you can see why this number right here would actually be a smaller number. Even though these are, the difference of these two numbers is going to be a smaller number than the difference of these two numbers because of the nature of the graph. This implies right here, f double prime less than 0 implies that f prime of x is increasing. Decreasing, excuse me. I'll put an arrow downwards, all right? So the function's increasing, but it's increasing at a decreasing rate, if that makes any sense. And so that, from a calculus point of view, this expression makes sense. It's very believable. However, we just proved it strictly by algebraic means. So this guy right here is the larger number. And that was what the original question was asking. Which one is larger? Okay, everybody. Hope you enjoyed.